Perfect. Hi, everyone. Welcome. Thank you so much for being here and for joining us in our second installment of our Amp Up Your Devices webinar series. It's a series that's showing examples of how our Fusion AX system can be used to study nanoelectronic devices in situ within the TEM. My name is Jen McConnell. I'm the product manager here at Protochips. Today we have an incredible speaker who will be talking about performing Hall measurements simultaneous to measuring magnetic domain patterns within the TEM. If you missed our last webinar, it was a great introduction to our Fusion AX system if you're not familiar with it, as well as some of its unique capabilities and the importance in situ TEM plays in electronic device research, especially as devices continue to get smaller and smaller over time. We have several webinars upcoming over the next few months as well, so be sure to register for them now so you don't forget. I do have a link in the chat box taking you to the registration page, and all the webinars are free. Share it with your friends, and so you'll get reminders as they get closer because it's about one a month for the next few months. So a couple housekeeping items before I hand it over to our star of the show today. Everyone is muted due to the audience size and just for unexpected interruptions to keep those at a minimum. But we will have a question and answer session at the end. So please put your questions in the questions box. There's a box specific to questions, and I'll help with the question and answer session at the end of the presentation. We will also have a survey that pops up at the end, and we'd really appreciate it if you could take just 1 minute to fill it out. It will be very helpful to us. Okay, so enough of that. Let me introduce you to our speaker today. Today we've got Dr. Darius Pohl. Dr. Pohl is a distinguished physicist specializing in nanotechnology and high-resolution transmission electron microscopy. He earned his physics degree from the Technical University of Dresden and completed his PhD jointly at TU Dresden and IFW Dresden. Currently, he's serving as a senior scientist and deputy director at the Dresden Center for Nanoanalysis, or DCN, at the Technical University of Dresden. And his research explores advanced TEM methodologies, magnetic nanoscale properties, electron beam shaping, and atomic scale structure property relationships. His contributions have been recognized with awards such as the 2017 IMW Research Award, the 2018 M&M Postdoctoral Scholar Award, and the MC 2021 Best Poster Award on Instrumentation and Methods for EMCD. So through his work, he continues to push the boundaries of materials characterization and nanotechnology innovation, and his presentation today is going to be no different than that description. So Dr. Pohl, thank you so much for joining us today. We really appreciate it. The floor is all yours whenever you're ready to start.
Yeah, thank you, Jen, for the very nice introduction. So today I want to explore nanoscale magnetism and show you our new in-situ setup for magneto-transport in a TEM. So all this work was done during the SPP 2137 Skyrmionics project, and is a collaboration of the Technical University, the IFW in Dresden, and the Max Planck Institute. So a lot of people contributed to the results, which I will show you here today. After giving you a short introduction about the idea and the motivation why we came up with such a new setup to measure magneto-transport in a TEM, I will go to explain the setup in detail, the calibration of the Lorentz TEM mode, the automatization, and then come to the experimental results, where we will first talk about a proof of principle experiment on a thin nickel film, highlighting the possibilities of our new setup, and then go to a more complex material system, which is really under debate at the moment. It's a manganese platinum tin Heusler alloy, which shows very interesting magnetic textures like skyrmions and anti-skyrmions. And there we are hunting for the so-called topological Hall effect. So what defines the magnetic state of a sample? So you see here 3 Lorentz TEM images of exactly the same sample, but of course the image looks completely different, right? So on the left-hand side, you see some stripe pattern. these stripes are perpendicular to each other. You have bright and dark contrast. And then in the central image, you see rectangular features popping up. They are as well regular arranged. And on the right-hand side, you see features which are more spherical or half a spherical, half a elliptical shape, and are as well quite symmetrically arranged. So how does the material, or how is this state defined which leads to this magnetic features? And to go there a bit more into detail and to understand that a bit more, we need to have a look at the total energy of the system. And this is one of the only formula I will show here in this talk. So this is a formula describing the total energy of a magnetic sample, and it has several contributions, and I try to get you a bit of feeling for these different contributions to the total energy, which then defines the magnetic state of the sample in the end. So starting with one easy part is the exchange energy. So if we assume a magnetic state like this one here in the bottom, so we have 6 magnetic moments, and they are just aligned like that in the starting configuration. And if we have energy simply having the exchange energy, and we want to minimize now the exchange energy of that system, we will end up with a magnetic configuration which looks like that. So all the magnetic moments are aligned parallel to each other and slightly declined depending on the starting configuration. If we have a system which has anisotropy, magnetic anisotropy, which is described here by that formula, so having an anisotropy constant, the magnetization of the system, and the unit vector of the anisotropy of the system. And how does that look like if you have magnetic moment configuration like that here in the bottom? So I made it in a way that 2 magnetic moments are pointed to the left, 2 to the right. And if we minimize the energy with respect to an anisotropy, which is pointing in a diagonal direction here, the system will end up in a state which looks like that, with 2 magnetic moments, with the moments aligned parallel to the anisotropy axis, and depending on the starting configuration, 2 are pointing down and 2 are pointing up. Then we have something very important for modern materials, which are skyrmions and anti-skyrmions, which is the so-called Chalochinski-Morier energy, or Chalochinski-Morier interaction, short DMI. And this is an energy which favors perpendicular aligned magnetic moments, which you see here by the cross product of the magnetization and the gradient of the magnetization multiplied with the Chalochinski-Morier interaction constant. And if we again take a magnetic configuration, starting configuration like that, minimize the energy, we will end up with a magnetic configuration which looks like that. So the magnetic moments try to align perpendicular to each other in order to minimize energy. And then we have the demagnetization energy, of course, which leads to the formation of domains pattern and closed domains at surfaces, for example. But the main thing which we can control externally and which gives us some knob to adjust the magnetic configuration of the sample is the so-called Zeeman energy, which depends, of course, on the magnetization of the sample multiplied by the external magnetic field. And if we have a magnetization state which looks like that, and we apply a magnetic field, of course, the magnetic moments will align to minimize the total energy, will align with the external magnetic field. And all of this have a strong interplay, of course. You can have different constants for the exchange energy, different anisotropy constants, different values of the Chalochinski-Morier interaction, and this will then define the material properties and the magnetic properties of your sample. If you want to dig a bit more into playing with magnetic samples and geometries, I highly recommend visiting this website here. It's Ubermag, which is the micromagnetic simulation software, which you can run in the browser, which on the one hand side minimize then this Hamiltonian, this energy, but you can also use then the outcome to use to simulate Lorentz TEM images or phases, magnetic phase images for holography or anything else. So how are magnetic properties measured via magneto-transport? Normally you guys have such a device like that, like a cryostat, a PPMS, and you shape your sample like that you have contacts on that where you run a current through and measure voltages. And what was found, for example, for such materials here is from one of my colleagues, that if you measure the Hall resistivity for different sample thicknesses, the magnetic properties which you measure here by that curve, by measuring the Hall resistivity as a function of magnetic field, dramatically depends on the thickness of your material which you want to measure. So there are different contributions to that measurements which you cannot directly see from simply measuring magneto-transport in such a device. And then if you look at the sample, so a thick sample have a shape which looks like that, quite smooth. But if you go to smaller thicknesses, you see some loops here popping up, and the question arises: what are these loops? What different magnetic states arise here? And this is quite hard to tell if you simply have only such a measurement. And it also shows us that the sample geometry has a strong impact on the magnetic properties. And that brought us to the motivation of our research here of designing such a new in situ magneto-transport measurement platform. We have magnetic textures, which strongly depends on the sample shape and the thickness due to non-negligible dipole-dipole interactions or surface interface anisotropies. And if we now image them in the TEM and compare them to magneto-transport measurements, for example, these measurements are then done on different samples. So this seems to be problematic, since for magneto-transport measurement, you need quite large samples to really contact them. And in a TEM, as you all know, we need quite thin samples at a very small area. So that led us to the idea to really do such experiments on the identical sample and to came up with a in situ magneto-transport setup in the TEM. So we want to combine here two techniques. On the one hand side, transmission electron microscopy, as you might all know, and on the other hand, magneto-transport setup. Of course, the TEM has the power of going up to atomic scale imaging. We can use very high resolution magnetic imaging using, for example, Lorentz TEM. We can do spectroscopy to analyze our sample to see if we have some segregation of different elements, to analyze the composition of our sample. We can do diffraction, which is very important to see how the grain orientation is, or if we reach the right crystal structure of our material. And on the other hand side, we have dedicated devices to measure magnetic properties in a cryostat, where we can apply magnetic fields up to 14 Tesla. We have a very large temperature range going from 2 Kelvin up to 400 Kelvin, normally even higher if needed. It's quite easy to contact your samples with electrical contacts, which are normally more than 10. And of course, you have different type of probes which you can use, like vibrating sample magnetometer. You have a Hall setup. etc. So what are the important techniques which we want to combine here out of these two worlds in the beginning? On the one hand side, in the TEM, this is the Lorentz microscopy, and this is a technique in TEM which is sensitive to the in-plane magnetic induction of your sample. And this is shown here on the left-hand side on the sketch for a magnetic sample with two domains. One is which is depicted here by the arrows. One is pointing to the back, one is pointing to the front. And due to this magnetic domains and the electrons interacting with the magnetization of that sample due to the Lorentz force, we have a deflection of the electrons, which is different depending on where you are in the sample on the domain. And that leads then to a contrast if you go to either overfocus as a dark contrast at the location of the domain wall, and in underfocus as a bright contrast in the image. And in reality, this is shown here on the right-hand side, an experiment performed on iron germanium, material which also shows skyrmion lattice. And you can see that in overfocus, the skyrmion pops up as a bright point, whereas in underfocus, we see that the skyrmion is black, shows a black shape, a black contrast with a hexagonal pattern arrangement. This is one technique we want to use to image the magnetic structure of the sample, which is sensitive to the in-plane magnetic induction. On the other hand, we want to use the so-called Hall effect, which is shown here as a sketch in the center. So we have our magnetic sample, or a sample in general, which we contact with at least 4 contacts. 2 we use to run a current through the sample, here from bottom to top. And perpendicular to that, we will measure with 2 contacts the so-called Hall voltage. And then we can apply a magnetic field perpendicular to the sample, so to the current direction. And then we have on the one hand side the so-called ordinary Hall effect, which is mainly proportional to the applied field, so linear proportion. And then we have, which is more important for us in the experiments I will show today, the so-called anomalous Hall effect, which mainly pops up in ferromagnets and which is proportional to the magnetization of your sample. And one example is shown here on the bottom. So you see the Hall voltage as a function of the applied magnetic field. And you can see for that sample, it linear increases up to the saturation of the sample, and then with the hysteresis come back to 0. So with this technique, we can measure now the magnetization of our sample as a function of the magnetic field. So as you see, we need to apply a magnetic field in order to measure the hysteresis of our sample. And in the electron microscope, this can be done by using the objective lens. The objective lens is a quite strong magnetic lens, which can apply magnetic fields up to 2 Tesla out of plane with respect to the sample. So similar like is shown here in the sketch in the center. But if we change the magnetic field, or if we change the excitation of our objective lens, of course, the TEM in general is not made for that. So there are different things we need to take care of. First of all, we want to know how large is the magnetic field which we generate at the area of our sample. And that is measured here using a standard commercially available Hall sensor shown here in the image in the inset on the top. So we use that Hall sensor, we calibrated it in a cryostat. These Hall sensors are linear in response with the applied magnetic field. So this is quite nice. But you still need to know the calibration, of course. So we calibrated it, then we mounted it into our TEM using the fusion holder and measured the magnetic field as a function of the objective lens excitation. That is what is plotted here on the bottom. And you see that we have a very nice, more or less linear behavior for small excitations, and then starting to saturate for higher excitation when we reaches magnetic field values up to 2 Tesla, where probably the pole piece starts to saturate then, and that's why we're going into the saturation also of the generation of the magnetic fields. But if we change the main lens of the electron microscope, of course we will have a strong impact on the beam itself, on the image, on the magnification, and so on. So that we also need to take care of, and that is shown here on the right-hand side, where we will start with looking at the image rotation as a function of the magnetic field. And you see that when we apply a magnetic field, as we expect, we have an image rotation which is linear with the applied magnetic field. So that is quite easy to compensate afterwards in the post-processing of our experiment. Another thing we need to take care of is a variation in the magnification of our image. You can see that by looking at that cross-grating, which you used here for calibration, that the distance is different for 0 magnetic field as compared to 600 milli-Tesla, that the spacing get larger and we have an increase of magnification in the order of up to 10%. But since we calibrated that as a function of the magnetic field, also that can be used for rescaling the images then in a post-processing. Since we're changing the objective lens and we're changing therefore also beam deflections and shifts and so on, we needed to calibrate the beam shift, which is in our microscope. So it's a GL F200 called BA1. The BA2 is the tilt of the beam. We have an image shift as well, and we have a slight defocus or focus focusing lens, the mini objective lens, and all of them are calibrated as well as a function of the magnetic field. So this was done by hand, reshifting the beam, for example, recalibrating the microscope for different settings of the magnetic field value. And if you do so, we ended up with functions for the different shifts and tilts and defoci. And we saw that this can be nicely described by polynomials up to a second order, so either linear or quadratic, with different coefficients as a function of the magnetic field. And having these calibration curves using a Python code, we can then apply any magnetic field and directly compensate shifts and tilts and defocus of our lens system to have a stable imaging conditions for our different field sweeps, for example. All that is integrated into a Python-based user interface where you can put in sample name and so on, user. But what is more important is the so-called sweep generator, which now combines our two different tools, so the TEM on the one hand side and the magneto-transport measurement devices on the other hand side, where you define the magnetic field generated by the objective lens. You define the current which will run through your sample. You will define the measurement points, the accuracy, the waiting times, and so on. And then running the experiment, we then can live see in a live plot how, for example, the voltage depends on the magnetic field of our sample. having all that set up, we started with a proof of principle experiment on a thin nickel film. And to do so, we had to prepare our own E-chips here to really have a nice hole setup. So we started with silicon nitride, silicon nitride wafers, shown here in the image. Then we back etched the silicon nitride. We etched away the silicon with KOH. And then we did photolithography to define areas where we want to have our nickel film deposited on the silicon nitride, and which is shown here as the mask layout on the right hand side. So the blue is now our nickel layout of the nickel film we want to measure. Then we deposited the nickel, did a lift off, then we did again lithography to define now the different electrical leads and contact pads, where we use now here 4 of our contact pads to contact the sample. And then we did the chrome gold sputtering process and the lift off again. All that is then mounted in our prototype fusion select holder which has 6 contacts. As I told you here in the design, we're using the 4 outermost contacts to run a current through our sample and measure perpendicular to that the voltage. And that you can see here on the top end, on the top image. This is a TEM image now, where you see the 40 nanometer nickel film. You see the contacts on both sides to run a current through the nickel film. And perpendicular to that, we will measure the voltage then as a function of the magnetic field. And if we do so, we will then simultaneously, for every magnetic field value, acquire a Lorentz TEM image and measure the Hall voltage. And this is shown here on the right-hand side. So let me first guide you through the images. You see now in the Lorentz TEM images, different domain patterns popping up here. You can differentiate between the domains by this bright and dark lines here, the domain walls. And what you can see is that when we increase the magnetic field from 18, 37, 56 up to 75 millitesla, that these domain patterns are vanishing. And at the same time, we now measure the Hall voltage as shown here on the bottom with the red points. And we see that when we increase the magnetic field, we increase the Hall voltage up to the saturation. And then if we come back with the magnetic field, we see the hysteresis and dropping down the Hall voltage again. And if we have a look at the variation of the Hall voltage in saturation, we can learn something about the accuracy of our measurement. And from that, we see that we have accuracy of roughly 6 nanovolts root mean squared for that setup, for that measurement setup and the current we applied here. But this was quite trivial, and we want to learn a bit more about our sample. And we looked at the outer part of the nickel film, and then we found some so-called speckle type of pattern, some magnetic contrast, which I plotted here in a higher resolution for different field values, now shown as percentage of the saturation magnetization, since this is now easier to compare than with simulation, which I will do on the next slide. So what we see here in the zoom in is that this pattern, this black and white pattern, starts to vanish at roughly 60% of saturation, and then goes over to this standard finer pattern, which stems simply from the underlying silicon nitride window. So we thought, okay, how can we understand that? Let's start to simulate the system using micromagnetic simulation. And since nickel is a well-known material, we can directly put in the material parameters like the saturation, magnetization, and the film thickness. And what we found is that the simulation of a continuous nickel film seems to be completely off when we compare the whole voltage of our measured film to the simulation. And that was quite surprising. And you can then say, okay, let's just reduce the saturation magnetization or play with thickness or so to just get a match between these two curves. That is what is often done in the magneto-transport community. But we thought let's use the power which we have, since we have the sample in the transmission electron microscope, and let's study in more detail how our sample really looks like. So we did high resolution STEM imaging, so scanning transmission electron microscopy, here in a HADF setup, where you can then see the nickel film popping up as brighter contrast as compared to the background. And by directly looking at that image, you will directly see that it's not a continuous film, right? It's more a granular film with small particles forming larger islands then of up to 50 nanometers. That you can either see by looking at the HADF intensity profile or directly by looking at the image itself. So this is like not a continuous film as we assumed for simulation. So we thought, okay, let's use that information to generate a binary mask in order to simulate now this different behavior of the coupling of the different grains, to understand in more detail how the magnetization now changes when we have such a pattern instead of a continuous nickel film. And if we assume the granular morphology and slightly only remove the saturation magnetization due to oxidation of the film, then we have a nicely fit of the simulation and our experimental measured hole voltage. And then we can use the micromagnetic simulation also to simulate now the Lorentz TEM images, and that is shown here on the right hand side, the simulated Lorentz TEM images. And this is the magnetic configuration, so the out of plane magnetization, color coded, and the in plane magnetization color coded. And this shows that the speckle pattern which we have seen in the Lorentz TEM images is nicely reproduced here by this granular morphology, and starts then to vanish when we go towards saturation of the thin nickel film. So this very successful showed that using the combination of hole measurements and Lorentz TEM gives new insights into the structure property relations of magnetic materials. So with this knowledge and the proof that our setup is working quite well, is very powerful, we wanted to start a second system, the inverse Heusler compound manganese platinum tin, where you can see here on the left hand side the crystal structure, and it has a broken inversion symmetry and therefore an anisotropic Chalchinski-Morier interaction. And now, due to the dipole-dipole interaction and with varying sample geometries, we have a very large zoo of different magnetic textures which appear in that material, starting from the helical phase in the ground state to skyrmions at lower temperature. It's of course a saturated ferromagnet for high magnetic fields, and at room temperature. So that what makes it interesting for us, it hosts anti-skyrmions as well as non-topological bubbles, and especially the anti-skyrmions. For that, the Hall signature of these anti-skyrmions is still under debate, and this is due to the topological winding number of these magnetic textures, and I will come to that in a second. But first I want to explain to you how we prepared the sample here, since this is a bulk single crystal, and we cannot spot a deposit such a material and then do the lithography. Instead, we need to cut out small pieces, lamellas, out of the material, out of that bulk single crystal, where then we have a large FIB fib lamella, which need to be very homogeneous and especially with the same thickness, if possible, and very low thickness of 100 to 150 nanometers over the whole lamella. Then we place this onto the commercially available 4-contact E-chip, where we cut in a small hole in the center. I hope I'm still okay. Just shows me that there's a problem with my internet connection. Let's hope everything is fine.
We still hear and see everything okay.
All right, okay.
Yeah.
So we cut a small hole in the center in order to have a better contrast then later on for the Lorentz TEM imaging. And then we placed the lamella there and contacted it. And then the whole setup in the end looks like that, where we can apply in one direction the current and measure perpendicular to that the whole wattage. And all that is then, of course, mounted in our transport holder. So let me show the first experiment we've done on that sample, which is applying a magnetic field up to the saturation, measuring the whole wattage, and just see how the sample reacts on different magnetic fields. And this is shown here on the right-hand side. I will run that video twice so that you get an impression. You see we are now in saturation. Nothing is changing so far anymore. And then the magnetic text just pops up again. So let's run that again with a bit more detail. So you see we have different contrasts here in the Lorentz TEM images. We have some stripes either in this direction or perpendicular. We see, since it's a single crystal, we see some bending contours here in the image as well popping up. And if I will now run the video again, increasing the magnetic field value, we will see that the spacing of these stripe patterns here will increase. Just before saturation, we will see the appearance of some magnetic textures like non-topologic bubbles and anti-skyrmions. Then we will have the saturation, and then when we come back at a certain field value in the hysteresis loop, we will see again these stripe domain patterns popping up and going back to zero field. So you see the increase of the distance here. You see the appearance of some magnetic features. This is the saturation, only the bending contours are still visible. And there is again the stripe domain pattern. So this seems to be very dominant here, the stripe domain pattern, and we want to understand that in detail. So starting at low magnetic fields, we see different variants of these stripe domains, of these helical stripe domains. And if we increase the magnetic field, some of them are growing and growing even farther in one direction. But what is also obvious is that the spacing of these stripe domains is changing when we compare, for example, 200 and 300 millitesla. So there's a larger spacing at 300 millitesla. And we can, of course, plot that as a function of the magnetic field, which is shown here in that graph. So this is the normalized spacing as a function of the magnetic field. And you see it's slowly increasing, and then at some point it's exponentially growing. And that we can understand if we dig a bit into the literature by the so-called chiral-soliton lattice of the helical phase, starting in the ground state with a sinusoidal modulation of the spin structure in one direction where you have a certain length. And then if we apply the magnetic field, of course, one domain, one direction will be favored, as I described in the beginning, and we will have the growth of one region, and therefore we have an increase of the periodicity of these stripe patterns. And this can be described by the chiral-Solitine lattice model, which are elliptical integrals of the first and second order, which is shown here on the bottom. And if we use that equation and fit it to our experimental data, that fits quite well. And we can as well do then the micromagnetic simulation, and then the Lorentz TEM images and the simulation fits quite well to each other. So that quite well describes our material. But we also measure, of course, the Hall voltage. And now we're using that model where we know the magnetic configuration as a function of field. We see by just plotting the Z component that this does not fit to the Hall voltage which we measure. So there seems to be something missing. And only if we add an additional Siemens component to our model, we could nicely reproduce the experimental observed Hall signature and also find local minima which describe the hysteresis in our sample. So far we understand part of our hysteresis loop, starting from the magnetic ground state where we have a stripe domain phase which increases with increasing the magnetic field. Then at some certain magnetic field value, we approach a stronger than linear increase of the Hall voltage, and that levels off with the appearance of non-topologic bubbles and anti-skyrmions with increasing fields. Of course, this is not included in the CSL model. And this discrepancy where it levels off is of the order of 500 nanovolts. And this is what I want to discuss now in more detail. In the literature, this is said to be the so-called topological Hall effect. And the theory predicts the occurrence of emergent magnetic fields from these skyrmions, from these topological spin textures with non-zero winding numbers. And this is just shown here in this illustration, in this sketch, that if you have a skyrmion, this is an skyrmion in that example, and if a current, an electron flowing through, you have an additional component of deflection by that topological spin texture on the electron flow. And this is called the topological Hall effect, which comes in addition to the already existing anomalous Hall effect. Describing the textures now a bit more into detail, which we see in our experiment on the manganese platinum tin sample. One is the so-called anti-skyrmion, which has this square-like structure, which you can see here in the LTEM image, where if we look at the magnetization of that feature, which is shown here on the right-hand side, it also has this square-like structure with the field going in, going out, here going in and going out again. And then we have the so-called non-topological bubbles, which are shown here in LTEM images on the bottom, a bit more blurry. They show up in different directions. That's why we have different type, either showing to the right, to the bottom, to the left. But they all have these magnetic configuration, which are this half elliptical shape. And if we use micromagnetic simulations again, we can simulate the structures of an anti-skyrmion and a non-topological bubble. And what is plotted here is the Z component, color-coded from -1 to 1 of the magnetization, and then the arrows point the direction of the magnetization. And this for the anti-skyrmion and non-topological bubble. So what can we learn from that micromagnetic simulation? Well, first thing what we can do is we can calculate the so-called topological charge. That is done by this equation here. So it needs to take the magnetization at one point and then the cross product of the derivative with respect to x and y. So this gives you, if you and the integration of the whole object, this gives you then a quantity how often the magnetization can be wrapped up onto a unit sphere. So for that object, the anti-skyrmions, that ends up equal 1. And for the non-topological bubble, that's why it's called non-topological. If we apply this equation, this one will not show, will not have a topological charge, topological winding number, or however you want to call it. But what we also see from that micromagnetic simulation is that the Z component of the magnetization for both systems are nearly the same. And that is interesting because that is what we are sensitive in with the anomalous Hall effect. Since there we are sensitive to the out-of-plane magnetization of our sample. Whereas with the Lorentz TEM, we are sensitive to the in-plane magnetic induction of our sample, where we can see differences between these two magnetic features. So how can we set up now an experiment to measure an impact on the topological Hall effect of these different magnetic textures, since the anomalous Hall effect seems to be similar from strengths, since the out-of-plane magnetic component is the same. So what we thought of was to acquire a so-called tilt series, where we tilt the sample along that dashed line here. And by doing so and keeping the objective lens at the same value, we will have an in-plane, a change of the in-plane magnetic field, and that will transform anti-skyrmions and non-topological bubbles into each other. So I want to run that tilt series now for you to give you a feeling about how the experiment was done. So you see, we start with a sample which has mainly anti-skyrmions. You see the square-like features. What you also see are here the banding contours due to the crystallinity of the sample. And of course, if we will tilt the sample, you will see all these banding contours moving through the image area, which makes it a bit tricky to follow. But what you can also see is that we will lose at some points the anti-skyrmions. We will see the appearance of some non-topological bubbles, and then transform them back to anti-skyrmions when we tilt back. So we are tilting up to 20 degrees. You see now we only have non-topological bubbles. And then tilting back, at some point, the anti-skyrmions will pop up again because we reach the correct in-plane magnetic field. Here the anti-skyrmions pop up again. Some non-topological bubbles pop up again, and then we come back to the untilted starting stage. And then we started to analyze all that data, all that 400 images, and found different scenarios where we started with anti-skyrmions tilted towards higher tilt angles, where we lose the anti-skyrmions, go to non-topological bubbles, then tilt back towards the negative direction, coming back to an anti-skyrmion area for certain tilt angles, and then tilting back to the original tilt value. So we have the images, but at the same time, we can now analyze the images. And since it was not always possible to track the anti-skyrmions or the bubble features, we used here the ratio of the measured anti-skyrmions to non-topological bubble. and can therefore nicely define areas where the anti-skyrmions pop up, or in the forward tilt direction and the backward tilt direction. And at the same time now we measured the anomalous Hall effect, which is shown here in the central panel, which of course follow the cosine behavior, since we tilt a ferromagnetic sample and therefore get different out of plane components. That very well fits. But if you look here at the appearance of the anti-skyrmions, either at the black or at the red curve, we see no deviation of the Hall signal with the appearance of anti-skyrmions which have a topological charge. We can also subtract that cosine here, which gives then the relative residuum, but also there is no correlation between the appearance of anti-skyrmions and the residuum, subtracting simply the cosine behavior. So to sum up, there is no correlation between the anti-skyrmion non-topological ratio and the Hall voltage. We have an offset of 25 nanovolts between the forward and backward direction, which seems to be stemming from an additional magnetic texture which appeared during the tilt. The expected 500 nanovolts, which we found in the hysteresis loop, can not be explained by a topological Hall effect. In our case, the topological Hall effect must be smaller than 25 nanovolts, with our measurement accuracy lower than 6 nanovolts. With this, I want to sum up my talk. I thought to you that we came up with a new in-situ magneto-transport setup using the prototype fusion select holder and our TEM, applying fields up to 1.9 Tesla using the excitation of the objective lens. Using different electrical measurement units and Python scripting, we were able to automate the whole loop process, whole measurement process, and had at the same time access to the whole capability of our TEM, like analytical TEM, Lorentz TEM, DPC, even electron holography. For the manganese platinum tin system, I showed to you that we have an induced helical domain growth, which is stronger than a linear increase, which stems from the chiral-soliton lattice which appears. The anomalous Hall effect can be correlated with this chiral-soliton lattice, and it levels off upon the formation of non-topological bubbles and anti-skyrmion. However, there was no direct correlation of the anomalous Hall effect with the occurrence of anti-skyrmions. So from our point of view, it seems not that we can measure or see, or that there is a topological Hall effect in that system. With this, I thank you for your attention, and I'm open for discussion.
Thank you so much, Dr. Pohl. That was a great and really interesting presentation. So thank you for the time to take put it together and give it to us. I do have a few questions here. So if anybody else has any additional ones, please go ahead and enter them in the questions box, and I will relay them now. And if we run out of time for some reason, Dr. Pohl, I'll just connect you with anybody that has any additional questions, and
sure.
You can talk to them offline to help answer them if you'd like. Okay. So the first question that is here is, did your automations help address any artifacts such as beam shifts or anything with image magnification, focus changes that were caused by variation in objective lens excitation during the magnetic field application?
So if I got that correct, this question goes back to this slide here. Yes, so if you apply a magnetic field, so normally the microscope is tuned for either, let's say, normal TEM mode, right, where you're at 1.7, 1.8 Tesla, or at 0 magnetic field. And then if you increase the objective length, all that alignment is messed up and the beam is shifted and tilted. And what we then made is we went to, let's say, 50 millitesla, and the beam was shifted, and we shifted it back, and we noted down the values of the beam shift and beam tilt and defocus and so on. And this then leads to these calibration curves for the shifts and tilts, which follow nicely either linear behavior or quadratic behavior. And this is then used for automation which can be used for any field value which we apply then in our experiment.
Great. Thank you for going back to that slide. I figured that would
Sure.
be helpful for that. Next question is, do you have any tips for successful lamella deposition onto silicon nitride chips?
Ooh.
There's always people interested in fib deposition
Yes.
on chips.
I mean, it's always tricky. I mean, just look at the amount of lamellas which we prepared. Yeah. So what we came up is that it helps if you glue the needle not direct at the side but more on the top, so that you then nicely can place it down and then just rip it off the needle, not using the ion beam anymore, but just rip it off. Just use the adhesion of the lamella onto the membrane and just rip off the needle and then start to weld the sample on the lamella. And that is one of the tricks, but yeah, it takes a lot of practice, and we have a very good engineer who's doing that job for us, luckily. So
That's
yeah,
good. If you're able to dedicate your time to that, you get really good. We've got a couple of webinars on our YouTube, also from
yeah,
different researchers that also talk about specifically fib prep, and we've got one in this series as well.
right. I've seen
Talking
that
about
as
fib
well. Yeah,
prep. There's
yeah.
endless discussions to be had on it. So, but if you have the one who asked that question, if you have any additional questions, let me know, and I'll connect you with Dr. Pohl, who can maybe connect you with the fib technician for some
Sure,
insight. If that's okay.
definitely.
I have a couple of questions also. You mentioned using, and you guys created your own custom chips kind of towards the beginning, but then I think around slide 17 and 18, you mentioned using a commercially available chip, maybe one of ours for fusion. Did I
Correct.
understand that correctly, first of all? And how did you decide which chip to use where? Was it strictly just the sample shape itself, or?
Yes. So the first sample, the nickel, was spot deposited. So there we are more flexible in doing then the lithography by ourselves. The manganese platinum tin sample is a bulk single crystal, so we need to do the fib cutting, and that's why we then went for using the commercial available chips.
I see. Okay. They both were able to perform the experiments though, as you
Indeed.
needed, right?
Yes, yes.
Interesting. Okay,
Yeah.
great. And then, oh, another question here. Have you tested your technique with other complementary techniques such as eels?
Yes.
Okay,
Um, let's go a bit more into detail. Um, so since it's the normal protochips holder, what we have not yet implemented is running, for example, the hysteresis loop and acquiring eel spectra at the same time. In general, that is not a big thing, but so far I see, yeah, so far, I mean, there are possible experiments I can think of, but yeah, we haven't done that yet. But the microscope is still in normal condition. So what I've shown for the nickel sample, for example, um, the sample was in the microscope. We did STEM, we did eels there to measure the oxygen content and so on. So from that point of view, there are no limitations. It's just in the end a scripting how you combine these different methods for your experiment.
sorry, I switched my camera because I was
Sure.
glitching and about to disappear. And then I've got a question, I guess, kind of based off of that, and then we can wrap up here because I know we're at the end of the hour. Are you going to be continuing, because I know some of this was a proof of concept, are you going to be continuing experiments with the Hall and the magnetic measurements simultaneous like that? Is that something you're still working on?
Yes, yes. Yeah, we will strongly continue in this one with different materials. So there are a lot of interest in studying the materials in situ in the microscope for different magnetic setups, not now for the skyrmion systems anymore, but either for altermagnets, things like that. But what we really would love to do is even to go to lower temperatures, because a lot of magnetic phenomena appear when you go to lower temperatures, even lower than liquid nitrogen. So let's see where the journey goes with this one. This will then be interesting. But yeah,
Okay, that's
still
great.
a lot
I
of
was
work
just
to
going
do.
to ask what temperatures you were thinking. So you're thinking down to like liquid helium temperatures?
Yeah, that would be great. Yes.
Yeah. Are there any temperatures in between that would be of interest, you think, or is
I
liquid
mean,
helium?
already with liquid nitrogen, you get a much broader range of materials which get interesting then.
That's great.
And then, of course, if you have helium, you have just everything.
Yeah.
Yeah,
Yeah, yeah. Okay, well, great. Well, thank you again so much for your time today. If
lovely
any
pleasure.
additional questions come in, I'll be sure to connect them with you. We will be posting
Sure.
this up on our YouTube here soon for those who couldn't make it, so we'll be able to share it. But again, Dr. Pohl, thank you for your time. Thanks to everyone that
You're
joined
welcome.
us, all of your time zones. I hope everybody has a great day, and we'll talk to you soon. Thank you.
Bye bye.
Bye.